NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve a 3-by-3 linear system using a clean elimination strategy. Here is our system. We label the three equations: equation 1 in blue, equation 2 in orange, and equation 3 in purple. Our plan: build two new equations that eliminate the variable y. Step 1. Multiply equation 2 by 2 to match the coefficient of y in equation 1 in magnitude. That gives 4x plus 2y plus 2z equals 8. Now add equation 1 and the scaled equation 2. The negative 2y and positive 2y cancel. So the new second equation becomes 5x plus 5z equals 15. Next, eliminate y again, this time using equation 1 and equation 3. Adding them gives negative 2x plus z equals negative 3. This will serve as our new third equation. To eliminate z between the last two equations, multiply the third equation by negative 5. That yields 10x minus 5z equals 15. Add the second equation, and this scaled third equation. Z cancels perfectly, and we get 15x equals 30, which means x equals 2. Substitute x equals 2 into the second equation, 5x plus 5z equals 15. We find z equals 1. Finally, substitute x equals 2 and z equals 1 into equation 1. 2 minus 2y plus 3 times 1 equals 7. Solving gives y equals negative 1. So the solution to the system is x equals 2, y equals negative 1, and z equals 1. Here is the ordered triple. Example. Below is the system we will solve. We will match the order of steps. Isolate y from the second equation, substitute into the first and third, eliminate z, solve for x, then back substitute to find z and y. Step 1. From the second equation, we isolate y. 4x minus y equals negative 5, so y equals 4x plus 5. Step 2. Substitute y equals 4x plus 5 into the first and third equations. Then simplify exactly as shown. After simplifying the first, 2x minus 16x minus 20 plus 5z equals negative 33, so negative 14x plus 5z equals negative 13. For the third, negative 2x plus 8x plus 10 minus 3z equals 19, so 6x minus 3z equals 9. Step 3. Multiply the first simplified equation by 3 and the second by 5 to align the z terms. Then add the two equations to eliminate z. Step 4. Solve for x from negative 12x equals 6. Step 5. Plug x equals negative 1/2 into 6x minus 3z equals 9 to find z. Step 6. Use y equals 4x plus 5 with x equals negative 1/2 to compute y. Therefore, the final solution, exactly matching the process from the prompt, is x equals negative 1/2, y equals 3, and z equals negative 4. Is x equals negative 1/2, y equals 3, and z equals negative 4. In this example, we will solve a 3-by-3 linear system using pure elimination, following the exact step order shown on screen. First, display the word example, then the problem statement in bold orange latex. Step 1. Multiply the first equation by 3 and the second equation by 2, leaving the third unchanged. This preserves equality because we scale every term in an equation by the same non-zero number. Now show the scaled system. Step 2. Replace the first equation with the sum of the first and the third, and replace the second equation with the sum of the second and the third. Adding equations eliminates x immediately because 6x plus negative 6x equals 0 in both sums. Show the new system with x eliminated in the first two lines. Step 3. Replace the first of these two y and z equations with their sum. This cancels z because negative z plus positive z equals 0. That gives a single equation in y only. Step 4. Step 4. Solve for y from 13, y equals negative 104. Y equals negative 8. Step 5. Substitute y equals negative 8 into the second equation. Negative 3y plus z equals 22. Compute z. Negative 3 times negative 8 plus z equals 22, so z equals negative 2. Step 6. Use the third original equation to find x. Substitute y equals -8 and z equals -2 into -6x plus y minus 7z equals -12. We get -6x minus 8 minus 7 times -2 equals -12. So -6x plus 6 equals -12, giving x equals 3. Finally, we have the complete solution triple. The answer is x equals 3, y equals -8, and z equals -2. Here is the exact problem statement. First, we will find x plus y plus z. Next, we will evaluate x plus 2y plus 3z. Finally, we will determine x, y, and z. Step 1. Add all three equations. We get the sum of the left sides equals the sum of the right sides, which is 22. That becomes 2x plus 2, y plus 2z equals 22. Factor out the 2. Divide by 2 to get x plus y plus z equals 11. Step 2. Compute x plus 2, y plus 3z using only the given sums. Write x plus 2, y plus quantity 2, z plus z. Regroup as quantity x plus z plus 2 times quantity y plus z. Substitute the known sums x plus z is 10 and y plus z is 7. Therefore, x plus 2, y plus 3z equals 24. Step 3. Use the total sum to isolate each variable. First, parentheses x plus y parentheses plus z equals 11 gives 5 plus z equals 11, so z equals 6. Next, x plus parentheses y plus z parentheses equals 11 gives x plus 7 equals 11, so x equals 4. Finally, parentheses x plus z parentheses plus y equals 11 gives 10 plus y equals 11, so y equals 1. Summary. The total is 11. The requested linear combination equals 24. And the unique solution is x equals 4, y equals 1, and z equals 6. Here is the problem statement. We are given three equations and asked to find a specific reciprocal sum. The key idea: divide each equation by the product of its variables. This converts sums like x plus y into sums of reciprocals like 1 over x plus 1 over y. Start with the first equation. Divide both sides by xy. It simplifies to 1 over y plus 1 over x equals 7a. Now the second equation. Divide by yz. We get 1 over z plus 1 over y equals 2a. Finally, the third equation. Divide by xz. This yields 1 over z plus 1 over x equals 3a. Great. Now place the three reciprocal relations together and add them side by side. When we add them, each reciprocal appears exactly twice on the left. The right-hand side becomes 7a plus 2a plus 3a, which is 12a. Therefore, 2 times the desired sum 2a plus 3a, which is 12a. Therefore, 2 times the desired sum equals 12a. Divide by 2 to finish. Example. We will solve a reciprocal system to evaluate the expression 3 over x plus 2 over y plus 1 over z. Here are the three given equations. We will invert each one and separate the fractions to obtain sums of reciprocals. Step 1. Invert and split. From xy over x plus y equals 1/5. We get x plus y over xy equals 5, which becomes 1 over y plus 1 over x equals 5. From yz over y plus z equals 1/7, we get 1 over z plus 1 over y equals 7. From xz over x plus z equals 1/6, we get 1 over z plus 1 over x equals 6. Step 2. Rewrite the target. 3 over x plus 2 over y plus 1 over z can be regrouped as 2 over x plus 2 over y plus 1 over z plus 1 over x. That equals 2 times the quantity 1 over x plus 1 over y plus the quantity 1 over z plus 1 over x. Step 3. Substitute the values. The green pair 1 over x plus 1 over y equals 5, and the blue pair 1 over z plus 1 over x equals 6. Therefore, the expression equals 2 times 5 plus 6, which is 10 plus 6, or 16. So the value of 3 over x plus 2 over y plus 1 over z is 16. 5x minus 2y plus z equals 0. X plus y minus 3z equals 6. 2x minus y minus z equals 1. Step 1. Add the second and the third equations to eliminate y. The sum gives 3x minus 4z equals 7. Step 2. Now, double the second equation and add it to the first. 2 times the second equation is 2x plus 2, y minus 6, z equals 12. Adding the first equation cancels the y terms. We obtain 7x minus 5, z equals 12. Step 3. Use the two derived equations to solve for x and z. Multiply the first by 5 and the second by 4 to eliminate z. Subtract to get 13x equals 13, so x equals 1. Substitute into 3x minus 4z equals 7 to find z equals negative 1. Step 4. Use the middle original equation to find y. Substitute x equals 1 and z equals negative 1 into x plus y minus 3z equals 6. This gives y equals 2. Therefore, the solution, in the exact order we derived, is x equals 1, y equals 2, and z equals negative 1. Here is the system. We label each equation 1 through 5 on the right, exactly as shown. According to the algorithm, add all 5 equations together. This gives 6x plus 6, y plus 6z plus 6w plus 6u equals 186. Divide both sides by 6 to get x plus y plus z plus w plus u equals 31. We will call this new result equation 6. Now subtract equation 6 from equation 1 to isolate x. 2x plus y plus z plus w plus u minus the sum equals 6 minus 31, so x equals negative 25. Next, subtract equation 6 from equation 2 to isolate y. That gives y equals negative 19. From equation 3 minus equation 6 we isolate z. We get z equals negative 7. From equation 4 minus equation 6, the 2w term drops to a single w. That yields w equals 17. Finally, subtract equation 6 from equation 5 to isolate u. We obtain u equals 65. Collecting our results, here is the solution in vector form. As a quick check, add them all. Negative 25 plus negative 19 plus negative 7 plus 17 plus 65 equals 31, matching equation 6. Equation 6. Here is the system. We will color code each equation. The plan is to subtract pairs of equations to cancel x, y, z. First, subtract the first equation from the second. The x and x, y, z cancel, leaving z minus y equals 3. From that we get z equals y plus 3. Next, subtract the second equation from the third. Again, x, y, z cancels. We get y minus x equals 1. Therefore, x equals y minus 1. Now substitute x equals y minus 1 and z equals y plus 3 into the first equation. Expand the product carefully. Then simplify to a single cubic in y. We factor the cubic by grouping. Notice y equals 2 is a root, so we can factor out y minus 2. The factorization is y minus 2 times y squared plus 4, y plus 7 equals 0. The quadratic has negative discriminate, so the only real solution y plus 7 equals 0. The quadratic has negative discriminate, so the only real solution is y equals 2. Back substitute into x equals y minus 1 and z equals y plus 3. X equals 1. Z equals 5. Finally, verify in all 3 equations. 1 plus 2 plus 10 equals 13. 1 plus 5 plus 10 equals 16. 2 plus 5 plus 10 equals 17. The solution checks. Example. We will solve a system that features products of the variables. Watch the algebra flow step by step, and I will highlight the key ideas visually. Step 1. Write the given system exactly as stated. Each equation is a variable multiplied by the sum of the other 2 variables. Step 2. Add the 3 equations term by term. The left sides expand into all pairwise products twice. The right sides add to negative 14. Divide by 2 to obtain the sum of pairwise products. Step 3. Use that total to isolate each individual pairwise product. From xy plus x, z equals negative 1. Replace the sum with negative 7 to get y, z equals negative 6. Do the same with the other 2 equations to get x, z equals negative 3 and xy equals 2. Step 4. Multiply the 3 pairwise products together. On the left, that is xy times xz times yz, which equals x squared y squared z squared. On the right, -6 times -3 times 2 equals 36. Therefore, the square of xyz is 36, and xyz equals plus or minus 6. Step 5. Use xy equals 2, xz equals -3, and yz equals -6 with xyz equal to 6 first. From xyz divided by xy we get z equals 3. Then xz equals -3 gives x equals -1, and y equals -2. Next, repeat with xyz equal to -6. Then z equals -3, x equals 1, and y equals 2. Final answer. The system has two solutions, -1, -2, 3, and 1, 2, -3. In this example, we will solve a four-equation system and determine how many possible values the variable it can take. First, let me show you the system and the question. Step 1. From a times b equals 2, we can solve for a as 2 over b. From c times d equals 4, we can solve for c as 4 over d. Step 2. Substitute these into the second and fourth equations. That gives b plus 4 over d equals 3, and d plus 2 over b equals 5. Step 3. From d plus 2 over b equals 5, isolate d. That is, d equals 5 minus 2 over b. Step 4. Plug this expression for d into the equation b plus 4 over d equals 3. Step 5. Simplify the denominator. 5 minus 2 over b equals 5b minus 2 all over b. So 4 divided by that becomes 4b over 5b minus 2. Step 6. Multiply both sides by 5b minus 2 to clear the denominator. We get b times 5b minus 2 plus 4b equals 3 times 5b minus 2. Expanding gives 5b squared minus 2b plus 4b equals 15b minus 6. Bring everything to one side to get 5b squared minus 13b plus 6 equals 0. Step 7. Solve the quadratic. It factors as 5b minus 3 times b minus 2 equals 0. So b equals 3/5 or b equals 2. Now compute a using a equals 2 over b. When b equals 2, a equals 1. When b equals 3/5, a equals 10/3. Therefore, there are two possible values for a, 1, and 10/3. The count of possible values is 2. Here is the system. The equations are xy plus x, z equals -4. Y z plus x, y equals -1. xc plus c, y equals -9. All products are between the same three unknowns x, y, and z. Step 1. Add the three equations. When we add left sides and right sides, each pairwise product appears twice. That gives 2xy plus 2y z plus 2x, z equals -14. Divide by 2 to get the sum xy plus y z plus x, z equals -7. Step 2. Use the sum equal -7 to isolate each product. Take x z plus y z plus x, y equals -7. Replace x z plus y z by -9 from the third equation. That yields xy equals 2. Next, replace xy plus xz by -4. So yz is -3. Finally, replace yz plus xy by -1. So xz is -6. Step 3. Multiply the three results. xy times yz times xz equals 2 times -3 times -6, which is 36. That equals xyz squared. Therefore, xyz equals plus or minus 6. Step 4. Solve for the individual variables. From the ratios, y over x equals yz over xz equals 1/2, so y equals 1/2 x. Also, y over z equals xy over xz equals -1/3, so z equals -3/2 x. Use xy equals 2 with y equals 1/2 x to get x squared over 2 equals 2, which gives x squared equals 4, and x equals plus or minus 2. Substitute to get the two solutions. Here is a quick visual to remember the structure. Think of a triangle with x, y, and z at the corners, and the three edges carrying the given pairwise products. The algorithm you used was add to find the total of the three edges, isolate each edge, multiply to get the square of the product at the center, and then use ratios to walk back to the corner values. Final answer. The solutions are the ordered triples, 2, 1, negative 3, and negative 2, negative 1, 3. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.